Welcome guys to day 10 on mathematical induction. So I'm going to warn you now, this is going to be quite math heavy. There's going to be a lot of letters, a lot of concepts we're going to kind of apply together. Personally though, this is one of my favorite things to talk about, not necessarily for the content itself, but because of what you can do with the content. Hopefully you've already watched that video posted previously about just the introduction of what induction really means, so inductive versus deductive reasoning. If it helps you out, think like Sherlock Holmes, although he uses other kinds of reasoning, like abductive reasoning. But regardless, the point is you're using philosophy / logical arguments and kind of applying it to math in a sense. I'm going to use the domino example that the lady in the video mentioned just to kind of help us out here and just apply it more in the math context. So let's give it a shot. So mathematical induction requires technically three things. So you see that there's two conditions here, condition 1 and condition 2, but condition 2 is kind of twofold. So there's going to be three parts that we'll go through. Condition 1 is the easiest one, condition 2 is the hardest part. Once you have both of those, the whole thing becomes pretty straightforward. So let's lay down some kind of base rules here. Let's start off with our first example here. And if it kind of helps you, imagine as if we're doing proofs back from trig. If you remember when we were solving trig equations or verifying identities, you want to say, hey, I want the left-hand side to look like the right-hand side. One thing I told you guys a ton back then was make sure you only work on one side at a time. And the reason when we said that was we aren't assuming the two equations are the same. We can't say the left-hand side is equal to the right-hand side. We're saying that the left-hand side looks like the right-hand side. It's like me saying, making some sort of like statement or trying to make an argument. Say, for example, that what's a good example? Let's just something random out there. Let's just say I'm trying to prove that Mr. Park is capable for running president, right? I can't, in my argument, use that original phrase as a reasoning, if that makes sense. That's like circular logic. You know, like when your mom like calls you out for like things that you've done, and then she like loops back to like things in the past that never had anything to do with what you're talking about right now, but she's still using that emotional like circle to kind of like get you to feel guilty about whatever you did, right? That's sort of the idea there, okay? So, a couple things that we want to lay down here. We're going to call this left-hand side here the left-hand side, LHS, and we're going to call this portion here the right-hand side, RHS. 99% of the time, and I literally mean like almost all cases, you're going to want to start from the left-hand side to make it look like the right-hand side, okay? So, let's have that set there. Let's start with condition 1. So I'm going to say condition 1. We're going to put like 1 with a circle. We want to prove that this equation, the left-hand side and the right-hand side being equal, is true when n equals 1. So let's take a quick look at the left-hand side, just do a quick recap here. The left-hand side really is just the series, right? It's an arithmetic series where we're taking sigma n equals, we're going to start from 1 all the way up to whatever it's going to be. Let's just say in this case n for the scenario. We don't know what n is, and we're just going to say n there. Because remember, this is the summation notation where it's like if n is 1, right, we're going to put it's just 1, right? When n is 2, if there's two numbers, it's 1 plus 2. If n is 3, it's 1 plus 2 plus 3. So I'm going to leave that there. We're going to come back to that, revisit that in a second because it's going to help us out later on. But the idea is we want to prove this is true for the first case when n equals 1. When n equals 1, the left-hand side is just 1. That's the first term, right? On the right-hand side, or actually we should probably start with saying check n equals 1 is true. So 1, equal sign, question mark. We don't know if it's equal yet. Then now on the right-hand side over here, we're going to plug that n equals 1 in. So 1 times 1 plus 1 divided by 2. And the question is, do both sides equal the same thing? So often you've been so used to just saying equal sign without any sort of question mark over it, right? Here we're questioning, are they actually equal? I want to make that very clear. 1 equal sign, and then let's see here. And I'm going to put the question mark for now, and we can erase it when we see it actually works. To me, 1 times 2 over 2. Oh, okay, right-hand side is 1, left-hand side is 1. They are definitely equal to each other. Definitely equal to each other. Easiest case, you plug it into the left-hand side, you plug the right side. The hardest part probably for this part is figuring out what the left-hand side actually is going to be. So if it helps you think about, okay, when n is 1, or when it's the first case, when you're only dealing with one term, what is it going to be? Usually it ends up being just that first term, or you could plug it in for the n right there. That's sort of the hint. that we kind of gave you over here. So if you go down below to the second problem, you can kind of see, oh, the first term, if I just plug in 1 into that part right there, that'll probably give you what it is. Or in this one, if I write the summation notation, it's just going to be this. The summation of said term here is equal to that. It's another way to rewrite it. Okay, so we checked in. First condition, good to go. Easiest condition. Let's now step it up a little bit. What we want to check now is if n is equal to k plus 1, show k plus 1 is true on both sides. So another way to think about it is in the video, the lady mentioned, suppose you have some dominoes, right? And I'm going to kind of make a proof that sort of relates it to what we're doing right now. You're trying to prove that all the dominoes are going to fall. That's it. That's your only proof. Seems fairly straightforward, seems very basic, but there are a couple steps you need to take. First condition is you need to check to make sure, does the first domino fall over? Condition 1 is, does that domino fall? If it's true, we move on to the second condition. And the second condition actually relies on this. Normally and logically, for us to deduce that this will work out, is we have to say, oh, if the first one hits the second one, that means the second one fell over. And then we got to keep going. Then the second one hits the third one. So if I write it down, condition 1 is 1 falls. That's condition 1, right? Condition 2 means we need to do this for every domino. If 1 falls, 2 falls. So let's just put it this way. Where's my eraser? If 1 falls leads to 2 falls, then if the second one falls, it leads to the third one falling. And if the third one falls, the fourth one falls. You have to be descriptive and specific about this case. And so you have to do this over and over and over again. And so for you, you might say that's a waste of time, or really, you're just never going to finish it. Exactly, that's the point. It's never going to finish. So what we do is we do this elegant solution where we clump all this up, and all we literally say is, if 1 falls, or if a certain domino falls, then the next one has to fall. If a certain domino falls, so if the nth domino falls, then the next domino, which is mathematically, if I know the nth one, the next one is n plus 1. Then the n plus 1th, sounds kind of weird, but that's how it goes, domino will also fall. Notice how elegantly and how cleanly I just created that logical phrase there. Instead of doing every single scenario possible, I clumped it all together and just said, hey, if the current one falls, then the next one has to fall. That's just straight logic. And so with those two conditions, the first one falls, and the second condition is if one of them falls, the next one has to fall, then that means the final condition, or the final proof to say is true. All dominoes will end up falling. The same thing happens in this scenario, just in a more mathematical sense. So what we're saying here is we're going to prove that if n equals k, so I should really put this here, if n equals k and n equals k plus 1, and we know that k is going to quote-unquote fall, then we know that k plus 1 has to fall. Use that sort of domino analogy there. So here's what we're going to do. I'm going to be given this. I'm going to be given the fact that n equals k. So that means 1 plus 2 plus 3 plus ... plus, instead of n now we use k, equals, and replace everything else, k equals k plus 1 divided by 2. In other words, we're just kind of replacing the n with k, just so that we can now modulate things as we need. What you're trying to prove is that it works for the next term. 1 plus 2 plus 3 plus ... plus k plus what's the next term? K plus 1. And so the way we can now go about doing this is we now replace anytime we see k with k plus 1. Because remember, k plus 1 is simply just the next term. So anytime I see k in the previous one, we can now put it into this next one here. So I'm going to do it in my head real quick. You get k plus 1, and then you get k plus 2 divided by 2. Rewind that if you need to. This step is a little confusing for some folks, but I'm waiting for the part where it's going to be the real, like, oh, like that seems like a lot going on there. Okay. You're given that first statement, you're trying to prove the second one. Just like in geometry when you had proofs, right? We're just trying to go this methodically, just a little bit more in an algebraic step here. Okay. So how does one prove from the first given step down to the proof step? Here's how you do it. Take a look at the given, and then take a look at the proof step. And what I really mean is take a look at, come on, where's the highlighter? Take a look at this step and this step here, particularly on the left-hand side. What is the only difference? give you a second to kind of look there. If you said that the second one is adding the next term, bingo, that's it. All you need to do is add the next term to both sides. Again, it's not always going to be k plus 1. It depends on the scenario, right? So like over here, we notice that it's like 1, and then it's 1 plus 2, and then 1 plus 2 plus 3, and then 1 plus 2 plus 3 plus 4, right? So another way to write that is we're just going to say the next term. If I were to try to figure out what the next term is, it'd be 1 plus 2 plus 3 plus 4 plus ... plus n, right? What's the next term after that? Oh, arithmetically, we're just adding 1 to each prior term, so to speak. So then it's going to be plus n plus 1. How did you know? Well, here in the end, I can plug in n plus 1 because that's the next term, so to speak. I'll try doing this another way once we get to the part where it might blow your mind, so just hang tight for a second here. Okay, so what happens is, what we're going to do is we're going to take the given. Whoops, daisy. That's the given, right? I didn't change anything about the given. Given was, like, I could use it. I don't need to worry about messing with that, right? And what we're trying to do is we're trying to add the next term to both sides. And because that's legal, that's the addition property of equality. Whatever you add to one side, you can add to the other. So I'm going to add the next term. How do I find the next term? Well, if this is what we call the kth term, right? The k plus 1 term is just plugging k plus 1 into the previous term. Oh, well, that's easy. That's just k plus 1. I'll try doing an example where it's not as clear-cut like this one. I think the next example will help out with that. And so what happens is now what I'm going to do is I'm going to add this term to both sides. So again, we're stuck with the given, the right-hand side of the original given. And I'm going to add that k plus 1 term. Notice I didn't do anything illegal here. I started with my givens. Here's my given. Here's my given. I would prove that that was totally fine to utilize based on the first, the beginning of the entire thing here. And what we're just doing now is we're adding the next term to both sides. Just a heads up, a lot of websites will teach it a little bit differently than the way I do. And to which I say, sure, it works, but it's not robust. And what I'm saying is they're kind of like cheating in a sense, where they're saying, oh, like you can use the proven statement to use in the given statement like that. You can't do that. That's not how it works. This is technically the official way to go about it. So just a heads up, if you see some other tutorials out there that kind of talk about like a different way to kind of go about it, seems a little bit easier. It is quote unquote cheating. It's not logically robust. So from this point, we now take a look. We're like, oh, okay, this left-hand side looks like the proven statement. I didn't cheat. I didn't do anything illogical. I added something to both sides, and that's totally fine. That's totally feasible within our mathematical world. And all you gotta do now is hope that this right-hand side, you hope and pray that it turns out to look like the proven statement. So let's take that. Let's go with it. Well, in order to do that, what I do need to first do is make sure that the second term here is a fraction divided by 2. And so I can just multiply the top and bottom by 2. We get the same concept. And now let's add them together. So we get, FOIL that out or distribute it out, k squared plus k plus the 2k plus 2, all divided by 2. I just did all that mental math real quick. Make sure I'm not blocking. Good. So we're left with k squared plus 3k plus 2 is equal to 2. And I can realize that, oh, I can factor this out. We get k plus 1 times k plus 2, all divided by 2. Oh, looks like we can't do anything else, Mr. Wright. Let's go back for a second. Does that match exactly what we wanted to prove? Does that match exactly what we wanted to prove? Bingo. Good to go. And so, as some of you may remember, this means proof complete. Since technically you are doing a proof or a verification here, we're showing that this is true for all natural numbers n. Okay, now that seemed a little lengthy. As you get the pattern, you'll see how it goes. Let's try the second one here because it's a little bit different. Notice it's not n, it's 2n minus 1. So I'm going to try to help you guys out with a way we can see this. Let's make a little table here. Let's just say here's what we're going to say. This is like the nth term, and this is going to be like the value of the nth term. Make a little table here. So here I can clearly see the first one is 1, right? And again, I'm thinking about the sequence, not necessarily the series, so just brace yourself for that. We know that the first term, the value is 1, as I can see here. We see the second term, the value is 3. The third term, the value is 5. The fourth term, the value is 7, right? So if I continue this process, if I see that there's the nth term, how do I get from this number, for example, transfer that to that number or that value? The way we go about it is we can say 2n twice the value of n, or double the value of n, and subtract 1 from it. Try for every one of them. Double the number 1, subtract 1. Oh, you get 1. Double 2, subtract 1. You get 3. Double the 3, subtract 1. You get 5. And sorry, I was talking about these original first 3 terms here. And so if I want to try to find the n plus 1 term, or like the next term after this guy, all you got to do is replace n with the next version, n plus 1. So then we get 2 quantity n plus 1 minus 1. So if you distribute that all out, you get 2n plus 2 minus 1, so just plus 1. This is key for the next term that you add when you get the condition 2. Over here in the previous problem, right, when I said add the next term to both sides, we added this being the next term. This was the next term. What happens now is when you get to this part here, you're going to be adding this to both sides of the equation. Simplify things out on the right-hand side, try to factor, try to see whatever else happens there, and then you should be good to go. I think the hardest part that, like I mentioned, condition 2 is the hardest part, but another intricacy that some of you guys miss out on is knowing how to count. And again, I've mentioned this in previous videos, and it sounds weird for me to say that to you guys as high schoolers who are in math analysis and should know how to count. But it's also about knowing how to count and how to relate the certain term to the certain value. So hopefully this table helps out a little bit, where we're distinguishing, here is the term, or like the first term, the second term, the third term, the nth term. Here is the value of that term itself. Computer science folks might find this a little bit easier to see when we're talking about, say, like an array where index 0, index 1, index 2, we say that index 0 is the first term, index 1 is the second term. It gets a little complicated with, or sophisticated with the offset, but once you get used to it, it's not too bad. You just gotta live and breathe the language for a little bit, kind of play to that style. The same thing is happening here. We're saying the first term is 1, the second term is 3, third term is 5, fourth term is 7. How do I relate, almost like as if this is like my x and this is like my y, how do I relate the two? That's what we're kind of going with. Hopefully that helps a little bit to kind of piece things together. Try things out with the following proofs, ask questions, set it up in the way that I have demonstrated here as well. And for those of you complaining that this looks like a geometry proof, I'm not going to deny that it really is a geometry proof. But the idea is that when you take things logically step by step and you kind of see the beauty behind it, that's when you really get to appreciate it more. Again, like I said before, the reason why I nerd out about this is not that this in and of itself is useful. It's the fact that the way you think about how you process these things, that is the useful part about it. I've been preaching that to my students all throughout the school year, and I know very few of you actually believe me on that. But hindsight being 20/20, once you get to the other side, maybe you'll see what I'm talking about here. Regardless, try it out, give it a go, rewind if you need to, and hope that at least gave you a good start for mathematical induction.